We were looking at particularly though, very closely related to that is multiplication, okay? So like I said, anytime we introduce a new kind of quantity, you need to define the number system, how we actually do it. So multiplication with vectors works in a few different ways, right? It depends what exactly you're multiplying, okay? The first type of multiplication is by a scalar, right? And we distinguish between the two again, right? What's the difference between a vector and a scalar? A scalar has just magnitude, whereas a vector has magnitude and direction, right? So, for example, if I take lambda multiplied by xy, that's my, here's my vector, here's my scalar, right? This would become lambda x and lambda y, right? So, as a kind of an example, if you have this vector here, OA, could be 7, -1, right? If I'm taking some scalar, so we can take 4 O to A, right? That would be the same as 4 multiplied by 7 and -1. And so we multiply that number by the horizontal and vertical components, 28 and -4. That's all well and good. That's multiplication by a scalar, right? Where it gets tricky is when we introduce different types of multiplication, okay? Because this is a scalar multiplied by a vector, but what happens if I have two vectors multiplied together? Well, this is where I started to introduce something called the dot product, right? And kind of unhelpfully, it's actually called the scalar dot product. And the reason why that's called that is because the result that you get here is you end up with a scalar as well. Now, to try and understand where this comes from, if I have two vectors u and v, let's say x, right here, all right. U is equal to this vector, x1, y1, and v is equal to x2, y2. Right. So if I take the scalar dot product in this situation, what I end up with is I get something like this. What I do is I take these horizontal components and I multiply them together. So that'd be x1, x2. And I take these vertical components and I multiply them together, y1, y2, and you add them together, okay? That's kind of like a formulaic approach to this. Geometrically, what's kind of going on is that they say it's like directional growth. So you're kind of multiplying the magnitudes in some sense together. Like the x and y components, we're multiplying them together, and then we're combining them to see what's the value that we get. So again, as an example. Right, so how do we find the scalar dot product, right? Well, all we have to do is we say, all right, u dot v is equal to my horizontal components multiplied together, so 7 times -1, and adding the vertical components here, 3 times 6, and we just combine them together. So we get 11. Looks good. Cool. Questions about that?
Could you explain why it becomes scalar?
Well, so the idea with so there is actually another type of multiplication where it becomes another vector. It's called the cross product, but that's not quite in this course, so we kind of don't touch on that. The reason why this one becomes a scalar is we've kind of defined it in that way, and we're kind of seeing what we call directional growth. So like how much of a vector is in another, and then we kind of combine them together in some sense. I think it's really clear to see, for example, like if you have two vectors that are the same, right? If we take, for example, u is equal to, let's take, I don't know, 3, 2, right? And if I found the dot product of this, so I did u multiplied by itself, right? What would you end up with? Calculate it for me. What would u times u by itself be? Yeah, it would be, in some sense, right? We're multiplying them together. But like, calculate it for me and see what you get. So we get 9 plus 4. Yep, no, you're right. And that's 13, okay? What's significant about this? Well, what's significant is calculate the magnitude of this guy now. Because we take this x component here, 3 squared, and we add this y component here, 2 squared, we get square root of 13. That looks very similar, right? And this is in fact an identity. What we can say is that if I take these dot products here, so u multiplied by itself, it's actually the same as the magnitude of u all squared. Yeah, right. So that's kind of like a relationship which exists between the dot product and the magnitude. And it's kind of like why it's convenient to find the dot product in this way, right? It's talking about like how much of a vector is another in terms of its like directional growth, right? What happens when we combine the two. And so you can see very clearly, like when you take the two vectors which are the same and you put them together, you end up squaring the magnitude. So it's kind of a relationship which exists between the dot product and like its lengths as well, right?